For question 14, it asks about the ionization energies. You're identifying um, an element based on its ionization energies, whether it's a metal or a nonmetal, and even what group it's in. So let's take a look at element A. Element A has a big jump. In order to go from the first ionization energy, which is the amount of energy it takes to steal the first electron, that's not a lot. It's 500. The first electron's easy to steal. 500, one electron goes pretty easily, but taking the second electron takes a lot more energy. And that's because you're going into a deeper shell. So you're removing the first, really the only valence electron for A. Remember that if I were kind of sketch this out, I don't know which element A is, but if we have our elements kind of filled in, or our electrons kind of filled in like this, so we have 2, then we have 8 in the next one. What's basically being represented here is that this electron is plucked away, and that's how much energy it takes to do that. But in order to steal more or any other electrons from like the second, or I guess one closer energy level to the nucleus, so I would say this is, I would say another one. It takes a lot more energy because it's closer, it's held more tightly to the nucleus, and that's why this is a bigger jump. So what we immediately see here is that if you're taking one electron, whenever you take one electron and it's easy, you automatically need to think this is a metal, because ionizing metals is easier than ionizing nonmetals, because metals give up their electrons more easily. So let's take a look at something that's a really good study aid, which is the ptable.com. So if you click on properties and you look at the ionization energy, if you actually select ionization energy, it shows you the ionization energies of the elements. You're not going to have this available to you on the test, but recognize the general pattern. The first ionization energy of metals is pretty low. Like you have your group 1s, 500 and something, group 2s, 700. Those are relatively low. They're all under 1,000, even reaching into most of the D block and the F block. But notice that when you start going into the non-metals, it starts getting pretty high. So that's the first clue, is that non-metals are going to have high first ionization energies. Stealing an electron from a non-metal is hard anyways, and then stealing more is harder. Stealing your first electron from a metal is easy. And even the second one, you can also click on second one and seeing what they are. Stealing a second electron is always harder than stealing the first one, so that's why you're looking for that biggest jump. So what we have is a metal, and we know this is a metal because stealing the first electron doesn't take much energy at all, but then suddenly it takes a lot more energy. How do we know it's a group 1 metal? We know it's a group 1 metal because you're only taking the first electron. Remember, that's the valence electron in this case, is relatively easy to do. That means that there's only one electron kind of straggling on the outside edge anyway. So if you remember how the periodic table is set up, let's see, kind of like this. And you've got the D block and all that stuff. The D block is not going to be important, so we'll just kind of scratch it out for this purpose. And then you have the P block. 1, 2, 3, 4, 5, 6. Okay, you can count the number of tall columns. Those are called the main group elements, and that tells you how many valence electrons there are. 1 valence, 2 valence, skip the middle, 3, 4, 5, 6, 7, 8, with the exception of helium, which only has 2 because it's so tiny. But everybody below helium, so neon, argon, all that, have 8. The reason that you know that element 1 is a group 1, so it's going to be in this family, you know that it's group 1 because they have their 1 valence electron, and it's the only one out there, so it's easy to steal away. And that's what that little 500 represents. But suddenly taking the second one or anything in a lower shell takes so much more energy, and that's indicated by this humongous jump in the ionization energy. Also recognize that for element B, there's not a very large jump anywhere. I mean, it gets progressively harder as it should, but there's no major massive jump. So this means that it has more than 4 valence electrons, and that means that it's going to be a nonmetal. Number 15. Ugh, quantum numbers, they're back. And sometimes they still confuse me, so I always have to think about them. Which of the following is a valid set of quantum numbers for the last electron added to the electron configuration for iron? So I would personally write out the orbital diagram for iron. Um, and luckily, we have something we already worked on earlier for that. So I'm going to copy as many of these as I feel like. Iron reaches into the 3D. Perfect. Duplicate. Slide that on down. Okay, there we go. So I'm going to get rid of these and pretend like I drew them all out fresh. Okay, so we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then iron is in the 3D level. So if we go up to where the periodic table is and we find iron is in the 3D, 3D1, 3D2. Actually, highlight it so you can see 3D1, 3D2, 3D3, 3D4, 3D5, 3D6. So it would be, according to Hund's rule, it would be written out like this: 3D1, 3D2, 3D3, 3D4, 3D5, 3D6. This is iron. We see we have unpaired electrons, so it's paramagnetic. Okay, so this is iron's orbital diagram. I just drew in this one because it said what is the last electron added. So it's going to be this red one right here. First of all, you notice that this has a down arrow. So we're going to kind of skip and realize that down arrows are going to have an ms, which is the spin, of -1/2. So that means that this answer choice is out because that one has a +1/2 here. So that means that that would indicate an up spin. This is a down spin, so that answer choice doesn't make sense. But there are still 4 out of 5 answer choices that do make sense based just on the spin. So we can't rely just on that. Let's take a look at N. That one's always pretty easy. So we have that clearly iron resides, the last electron for iron resides in the 3D, which means that N is equal to 3. So N equals 4 is out. Now we have this issue of which L is it? So as a reminder, if you kind of look at the orbitals for D, we know that for D, it's denoted by L equals 2, which means that the little boxes, so to speak, or the lines, the orbitals are going to run from -2, -1, 0, 1, and 2. These purple lines that these purple numbers I just drew in, those represent the M subscript L. So we just drew in the red one, which means that it belongs to the ML of -2. So that makes sense. In addition to the fact that it's in the D orbital, and we just said D, L equals 2. So that part makes sense. So it's kind of like putting together multiple pieces. As a quick review, N equals 3 tells us that it's in the third principal level, and that makes sense. It is. This L equals 2 tells us it's in the D orbital, and it is. Because it's kind of, like I said up here, wherever I said it, I just recommend you memorize that because that makes it easy. So because it's in the D, L equals 2. Perfect. Then you got to ask yourself, well, what is ML? ML runs the gamut of -L to L. So if you realize that it's in the D orbital and L equals 2, then ML is going to be -2 to +2. So that's -2, -1, 0, 1, and 2. And because we drew in this electron, and we clearly drew it in according to the Hund's rule, we drew it in and it was downward spinning, and also it belonged to the -2 just based on how we did it correctly. That's why the ms is -1/2. By this point, you're probably over quantum numbers. I am. 16. Which ion is the largest? So when it comes to ions and their size, first, one of the things you kind of should remember, first of all, is isoelectronic. We talked about that. If something is isoelectronic, that means it has the same number of electrons. Now, some of these are certainly isoelectronic. I think actually all of them. I do not have the periodic table memorized. I'm just going to slide it over and do here. So go back to the normal periodic table. I'm just going to refresh the page. Okay. So we had a calcium 2+, so that's 20 - 2. That'd be 18 when it loses its 2 electrons. So 18 electrons in the calcium 2 plus ion. There was also potassium, which is normally 19 when it's neutral, but we lost an electron, so that's also going to be isoelectronic to argon. So right now we have calcium ion being isoelectronic to argon. We have the potassium ion being isoelectronic to argon. And then we have the sulfide ion, which I believe was -2. Yep, and that means, I guess I'll go this way. Which way did it go? There we go. Sulfide is normally 16 electrons when it's neutral, but we added 2 electrons, also isoelectronic to argon. We even have scandium, which is, let's see, 21. Normally, scandium has 21 electrons, but as we saw from the problem, it gained 3. So let's just do a quick check. We have 20 minus 2, that gives us 18. Here, we have 19 electrons normally, minus 1, it gives us 18. And then this scandium here is normally 21. We subtract 3 because it lost 3. That gives us also 18. And then we have the sulfide ion. Sulfur is normally 18. And we're adding 2. Okay, I cannot count today, it's fine. Normally it's 16 and we're adding 2 and it gives us 18. So as we said earlier, these are all however you spell that word. There we go. I could just move it on over. They're all isoelectronic. Now, from your rules, you remember that if you have an isoelectronic series, the largest one is going to be the one that gained the most electrons. So we have 2 electrons gained. And also, the reason that this is true is because electrons repel each other. They're all negatively charged. So this is losing 2 electrons. And this is losing 1 electron, and this is losing 3 electrons. But we do have something where we're gaining 2 electrons. So those extra 2 electrons are going to repel the 16 that were already there. And that's the reason why this one is largest. So the main takeaway here is that when you have an isoelectronic series, which basically means a bunch of stuff that has the same number of electrons when they've gained or lost, so they all have the same configuration now. When you have a series of isoelectronic species, the largest one will be the one that gained the electrons, or the one that gained the most electrons. So that's why this one's bigger. Anions are the largest when they're all isoelectronic. Now imagine flipping this question, and you had a bunch of negatively charged things and a single positively charged thing. Cations are going to be smallest because they lose electrons, so they shrink a little bit. Number 17, what is the electron configuration of the iron ion in iron 3 sulfate? All right, so kind of going way back to, I think, September, or I don't know, maybe September, late August, kind of splitting this apart, there are 2 iron ions. Now, iron is a transition metal, so it can assume multiple oxidation states or oxidation numbers. So we don't know the charge on this iron. Whenever we don't know the charge on the iron, we can come back to it. So that's why we look at this sulfur, or these sulfates. There are 3 sulfates. Sulfate is SO4, 2-. You do just have to remember your polyatomic ions. Sulfate is SO4, 2-. Now, if there are 3 packages of sulfate, and every sulfate is -2, that tells us that the negatively charged part of this compound is going to have a -6 because you have 3 times 2-. So there's a total of -6 electrons transferred, or 6 electrons transferred. So it's going to be -6 for the anion side. That means that if you flip it, there's got to be plus 6 charge on the iron side. That means that if there's a +6 charge, because remember, overall this is neutral, so if there's -6 over here, it's got to be +6 over here. If there is a +6 shared between 2 iron, that means that every iron is a +3. So the name of this would be this would be called iron 3 sulfate. Why did I just go through all that? The whole point of going through all that was to figure out what is the charge on this iron ion. This iron ion is an Fe with a 3 plus. Now, of course, there are two iron ions, but they're the same. So this is an Fe3 plus. What does that mean? Remember, when there's a positive charge, it's a cation, and that means that it has lost electrons. In this case, it has lost 3 electrons. So whatever the normal configuration is, whatever the normal electron configuration is for iron, this one's going to be 3 less. So let's, actually, I'll write out the normal configuration. No point in doing the orbital diagram right now. So let's do that. Iron is 1s2, 2s2, 2p6, 3s2, 3p6. Right now, I've gone all the way through 3p6, argon. Then we're going to jump down to 4s2, which gets us through, I believe, calcium. I should probably memorize the periodic table. There we go. Yeah, calcium. Then we go down to 3D. Finally, we're on the street that iron lives on. Actually, I'm going to go here. It's just faster. So iron lives on the 3D street. If you go to our little, this is actually fun to read anyways. If you find out where iron is 1, 2, 3, 4, 5, 6. Iron is 6 into the 3D. So it's 3D, 6. This is neutral iron, by the way. That's what iron is when it's neutral, because it's going to have the same number of protons as electrons. So we have our 26, I believe it's 26. Yeah, we have 26 protons, therefore it'd be 26 electrons when it's neutral. But we just said that this iron here is not neutral. It has lost 3 electrons. So what we're going to do is we're going to take our electron configuration. I'm going to duplicate it because I'm lazy. And realize that since this has lost 3 electrons, we're going to take 3 electrons out. Those 3 electrons are going to come from the highest energy level, starting with this 4s is going to blow up and go away because we're taking away 3 electrons. That gives us 2 gone. So let's get rid of that. Now we still have 1 more to take, and that's why this 3d6 is going to become a 3d5. So we've lost 3 electrons. We've lost the entire set of the 4s. So we lost 4s2 completely. And then we also have to take another one out. We had to take it from 3d. And that means it went from 3d6 to 3d5. So gone and gone, just so you can see how that transition worked. Now, of course, all your answer choices are using the abbreviated form. So in case you were wondering about that, argon is held within all of this. So if I wanted to do the abbreviated electron configuration for the iron 3 ion, it would look like this. I can replace all this blue stuff with argon. Make sure you recognize or remember how to do abbreviated configurations. And that's why this is your answer. Let's see. So consider the elements lithium, boron, and oxygen. Which element has the highest first ionization energy? Which element has the highest second ionization energy? So we talked about ionization energies, and basically it's how easy it is to steal an electron. You can think of that conceptually. So lithium is in the first family. It's kind of important to note. It's in group 1. And then boron, I don't remember. It is in group 3. It's across the pond, so it's in group 3. It's in the P block. And then you have oxygen, which is in group 6, also in the P block. So first of all, which one has the highest first ionization energy? There's an important trend that you should remember. Let's pretend like this is the periodic table. Okay, great. So one thing to recognize about atomic size is that size goes up as you go down. So larger atoms are going to be found in the bottom. So I'm going to say larger, smaller. That's the size trend for atomic size or atomic radius. Now, what's the trend going from left to right for size? That's going to be this. They get smaller because as you add protons, every proton kind of attracts the shells and the electron shells in a little bit more. So from left to right, atoms are going to shrink in size. It's larger and smaller. This is loosely but kind of strongly based on or related to the trend for ionization energy, because for ionization energy, smaller atoms are harder to steal from. So for ionization energy, I guess I'll label that as orange. That's the size. In general, you can relate size with ionization energy as being opposite trends. So for IE, we're gonna hold this the first IE only. They kind of relate, but anyways. For ionization energy, the ionization energy goes down as you go down, which basically says that as you steal electrons from larger and larger atoms, it gets easier and easier to do so because those electrons are farther and farther from the nucleus, which holds them. So we're going to say that the ionization energy is larger for those smaller atoms at the top, and then those larger atoms at the bottom of the periodic table, they have a smaller ionization energy. And then that trend is obviously reversed going from left to right as well. With that being said, we can kind of look at it and be like, well, lithium's pretty tiny. Lithium's over in this region over there. So because lithium is small, it has a relatively large ionization energy. However, it is in group 1. So stealing its first electron is pretty easy. So that means that for lithium, I'll say that lithium has a low first ionization energy. Let's talk about the why behind that. Lithium having a lower first ionization energy is because it is in group 1, so they only have one valence electron. Since they only have one valence electron, stealing that single valence electron is not very hard. Despite the fact that lithium is small, so stealing anything from it's a little bit of work, it only has that one valence electron. And then you're going to compare, we don't really care about boron, because boron's kind of in between. So go to the other extreme, and you have oxygen, which is in the same period. So it's going to be oxygen. Oxygen is smaller than lithium. So it's going to have a higher ionization energy. It's going to definitely have a higher first ionization energy. So first IE. So let's compare these two ping points just based on the initial or the first ionization energies. Why does lithium have a lower first ionization energy than oxygen does? It has just one valence electron, so stealing that one valence electron is easy. Oxygen has multiple valence electrons, and it's a smaller atom, so it's not as easy to steal the first one. So it has a higher first ionization energy based on its smaller size and the fact that it has other electrons in that outer shell. Now, what about the fact that lithium is going to have a higher second ionization energy? When you steal the second electron from oxygen, you are still you're still stealing from its valence shell. Like when you steal the first electron from oxygen, you're stealing its valence. But since oxygen has 6 valence electrons versus lithium's 1 valence electron, stealing oxygen's first one and its second one and its third one and its fourth one and its fifth one, you're still stealing from the same shell. So that's why it has the highest first ionization energy, because stealing from it at all is harder than for lithium. Now, what about the highest? Why does lithium have the highest second ionization energy? When you steal lithium's second electron, you've got to reach farther into the shells. Let's see, 1, 2, that's fine. So here is the first 2 electrons for lithium, and then here is its valence. Steal the first one, that's why it has a low first ionization energy. What happens if you steal the second one? You have to reach into a shell that's closer to the nucleus, and that's going to take more energy. So recognize, I guess that's a long way to say, recognize the trend between the energy levels. When you go into a deeper energy level that's closer to the nucleus, that's what I mean by deeper. That's where that big jump in ionization energies come from. And then also recognize the size trend within a period. That kind of helps you answer those questions. Okay, so this one's relatively simple. It just asks which element has this configuration. So the way that you can find them, if you assume the element is neutral, which all of these are all neutral, no pluses, no minuses, then it's super easy. Here's the trick. Just count up all the superscripts. 2 plus 2 plus 6 is 10, plus 2 is 12, plus another 6 is 18, plus these 5 is 23. So that means that there are, 26 electrons in this neutral element. Now, since there are 23 electrons in this neutral element, so you're going to go to the periodic table and you're going to find the 23rd element and you'll be like, oh, vanadium. Vanadium always has 23 electrons when it's neutral because it has 23 protons. 23 protons, 23 electrons. That means that they're equal and opposite for their pluses and their minuses. That's neutral vanadium. And this is an easy question because they're all neutral. You don't have to add or subtract any. This is the electron configuration for neutral vanadium. The way that you can figure it out quickly is you can just count up all the superscripts. However, you could also just point it out with your fingers on the periodic table. So here's what it looks like if you were to do it that way. Go back here, P table. Okay, so if you were to count it out, it'd be 1s2, that gets you all the way to helium. Then you get 2s2, that gets you to beryllium. 2p6 gets you down to neon. 3s2, 3p6, 4s2, 3d3. Verify that that makes sense there, and that's how you do it.